Okay, well, as you see, I'm Nigel Fox from the Optical Radiation Measurement Team at MPL in a division called Quality of Life, and I hope that you perceive that what we're talking about is quality of life, but it's also about commercial interests as well. It's not just climate change, but the measurement of the surface, the Earth, from space has many commercial applications. Well, what about Earth observation, certainty of data? Well, it is all about pretty pictures, and here you see a high-resolution image of the M25 galaxy. It's about climate change. Is it man-made? And I want to tell you about good measurements in space, that it's not rocket science to do good measurements in space. Well, maybe a bit. But this is MPL, and maybe you saw here I cheated, I lied. This was not the M25 galaxy. This is the Earth. This is London from a digital camera from the space station. And here you see Washington, D.C. And just to emphasize that it really is Washington, D.C., just want to show you what I find, and I must admit, we've all seen this many times, but I still find it amazing that from 500 miles up, the ability to view the Earth, and these are sensors that are viewing the Earth, which are civilian sensors, and I have no doubt that there is military capability that can do 10 times better than this. I still find that fascinating that we can do that from space. I'm sorry, but I just like that kind of concept. Okay. About monitoring and interpreting the Earth systems. Well, as we all know, the incoming solar radiation to the Earth drives the planet. It's important to us, but it's also damaging to the biosphere and human health in terms of ultraviolet. By measuring the solar reflected radiation, everything has a unique spectral signature, so that we're able to detect water pollution, we're able to detect atmospheric contaminants, we're able to detect the type of vegetation, minerals. Everything can be done simply by measuring the unique spectral signature of the reflectance of the Earth. And we can see the pollution here coming off the beaches in Sicily, but we can also use it to detect the plankton, the phytoplankton, and determine where's the best place to fish. So it's an incredibly powerful tool. We can determine the life cycle of wheat. When do we want to pick our wheat? When is there a problem with it? The subtle deviation that if, when I view this field, it's not as advanced as what it should be from the planting cycle, we know that there's stress, there's a problem, therefore we can go and do something about it. It gives us the ability, in principle, to measure the carbon sinks, how the carbon that we're producing, mankind is producing, is being absorbed by vegetation, increasing the vegetation, and in principle, our ability to detect the subtle changes in vegetation due to anthropogenic carbon. But we're starting to need uncertainties of a few tenths of a % in order to be able to measure the changes that are comparable with what we're putting into the atmosphere. These are really quite small uncertainties that we're seeking to achieve. And in the thermal band, we can measure the water temperature, we can look for forest fires, and we can look at the atmospheric chemistry. And I want to stress here, just to do spatial variability, to detect whether it's a field of grass or a field of wheat, we just need good short-term stability and signal-to-noise ratio from a single sensor. We can just do pretty pictures and do ratios. That we can do. But as soon as we need to do some long-term studies for climate change, we need to have accuracy and consistency, because we have to have this reliability over decades, not just 1 day, 5 days, 10 days. And you will find that most times on a specification of a satellite sensor, an optical sensor, they talk about signal-to-noise ratio and the ability to resolve a difference. It's hard to see how, when you want to do climate change, that signal-to-noise ratio should not equate to accuracy. The only reason it doesn't is because signal-to-noise ratios are 0.1% and accuracies are 10%. And therefore, actually, it's difficult to achieve what is reality. Okay, well, we may have all seen this film about what the impact of climate change is. It's all about the questions: is the Earth warming? What is the cause? Can we detect it? Can we stop it? This is just a plot showing the variation from different models as to what the temperature of the Earth will be by 2100. Pick your model, pick your data, pick your temperature. Which one would you like it to be? 2 degrees, 5 degrees, 10 degrees? Anything you like, because that's the quality of our ability to use models to predict climate temperature change. The impacts are phenomenal, and the difference in impacts are phenomenal, but we have no ability to make that judgment. I also want you to read that statement as well. Climate change in the last 50 years is likely to be anthropogenic in nature. This is from the International Panel of Climate Change, and its impact is far from clear. The term likely is defined. It's not just a phrase, it's a well-defined phrase. It's 66 to 90% probability. They could have chosen very likely or certain. They didn't. They chose likely. It's not a certainty that we have man-made anthropogenic change for climate. Why do we need to improve quality assurance of this data? Well, I've already mentioned climate change. It helps us to improve our prediction of weather systems. We all see Meteosat pictures on a routine basis. The ability to monitor the treaties. We're starting to trade carbon credits. How efficient are these carbon sinks? If someone plants 100,000 trees, do we know it's 100,000 or 99,000? Do we know that they're healthy? Do we know that the right type of trees? We need to be able to quantify these measures so that we can actually audit and police the process from above. We have the ability and the development of a marketplace called GMES, Global Monitoring for the Environment and Security. It's a European Union and ESA project which is about linking together sensors and data from the ground, from satellites, to get information which is of use to society, the ability to monitor disasters, not just from one sensor, but the ability to combine data. We need interoperability. What are the problems? Well, sensors are biased. We have different answers from different sensors. These are 3 sensors on different platforms. The difference between those two is 5%. Sorry, it's 10% in orbit. The science requires 3%. They measure the same thing and they get 10% difference, so you normalize one to the other. Pick the one that you choose. AVHRR is 20% different than those. Remember, I said we need to start measuring these measurements in the few tenths of a percent. This is the biases between these sensors. The instruments change on launch and degrade in orbit. Let's just emphasize this point here. This is looking at a desert in time using the same sensor or same type of sensor on different satellites. Should be a straight line. There is no vegetation in the desert. This is looking at vegetation growth. What you're seeing is changes in the sensor itself, and you're seeing step changes in launches between satellites. It's the greening of the desert is the argument that is used, but it's really showing you how poor the sensors actually are. I'm not looking to go through this whole set slide. It's just emphasizing every optical satellite that is launched degrades in orbit. Percents, 10%, 20%, pick your number. There is a problem that we need to have the ability to remove, get consistent statements of uncertainty. We need to have onboard calibration systems to be able to calibrate these things, but they're expensive, their reliability is questionable, and their traceability is questionable. Let me give you some examples. Is the sun getting hotter? This is total solar irradiance, the solar constant, with time measured from space. And as you can see, we have an 11-year solar cycle where we have a change every 11 years of about 0.1% in the output of the sun. It's a very regular cycle. It's an extremely stable monitoring, which is why we can say the sun is constant. That's the source data that made that up. I find it very hard to get that from that. Yes, I can normalize everything, which is what's done, and you can link everything together to give you this solar constant. But we're talking here of spreads of 0.7% in uncertainty. If you normalize, you can generate this, and you can argue you're looking for change. That's true. You lose any sensor and not have an overlap, you lose everything. You have no record. The longest climate change record is gone. Okay, could argue we're getting better. We're getting nice starts to getting consistent measurements over the last 5 years or so. Only about 0.1% variation. Problem is we launched another sensor 2 or 3 years ago and it comes off the curve. It's down here, claiming 0.02% uncertainty, difference of something like 0.4%. What's right? I don't know. Nobody knows. Does it matter when the sun is changing? Well, back in the 1680s, we had the Thames freezing. We had a mini ice age. This corresponded to 0.3% change in the output of the sun. 0.3%. We're getting variations in our absolute measurement of the sun to 0.7%. Therefore, maybe we want climate change. Maybe we want global warming because maybe the sun is going to cool again. It will. No question. It's a variable star. We're talking 0.3% change. Why is 0.3% so important? Well, it's not actually the 0.3. It's the fact that it's spectral in nature, and it's the spectral variation that's causing the problem. It's actually changing by some tens of percent in the UV, and it's that is really driving the interface with the oceans and the atmosphere. And arguably, if we can measure this spectral variation in space early enough, we can help to predict El Nino events. So it's a very powerful tool that we can do. Let me show you this one. This is input solar radiation coming onto the ground. About 23% is reflected by the atmosphere. About 20% is absorbed by the atmosphere. Another 8% reflected from the ground. And the rest of it's absorbed by the ground. So that's the energy balance that comes in. And we have emitted infrared radiation, as we all know. And then we have this natural greenhouse heating, which is feeding that back and keeping the Earth nice and warm. And then we have our greenhouse gases, which are causing the problem, hitting up 2.5 watts per square meter, very small fraction, but causing this major change. Problem is that actually this is modeled atmosphere absorption. What we actually measure is 80 watts per square meter. It's about 25% different than what we measure. Does that matter? That heating effect of that missing radiation is 10 times the heating effect of all greenhouse gases. Therefore, our models that we're using are really quite poor. So, how do we want to do to get reliable satellite data quality? We can do good pre-flight calibration, and we can do post-launch calibration to have an onboard calibration system, have abilities to compare with true ground reference physical parameters which we understand and which we know with complete certainty. But it's not just the instrument that matters, it's the models, it's the algorithms, it's the processing, the data transfer. Everything is critical in these sorts of systems, and we have to have the whole processing chain fully quality assured, fully audited and fully validated. And it's extremely rare for any of these activities to be independently reviewed or audited by anybody at this moment in time. So, what is the solution? We'll tell you about how we calibrate sensors on the ground, and I better start speeding up quite quickly. Okay, so what is the base reference for optical radiation measurement? What we have is a sensor which measures the heating effect of optical power. Electrical substitution, you put optical radiation onto something, gets absorbed, raises its temperature, you can measure the temperature with a thermometer. If you then switch off your light, put a heater to that surface, add the electrical power, and to get the same temperature rise, you can say electrical power equals optical power. That's a 100-year-old technology. What we did at MPL was cool it to cryogenic temperatures, and you gain uncertainties of a factor of 100, a factor of 50 from using this at room temperature to operating at cryogenic temperatures, and you increase your sensitivity by a factor of 1,000. This is just a photograph of such a sensor, and this is showing 30 years of these sensors in development at MPL. This is the traceability chain. We have our cryogenic radiometer, which is a black detector. As I've described, it will measure all radiation equally, but if we use monochromatic radiation going into it, we can determine spectral response, and from that we can determine measurements of spectral radiometry, photometry, pyrometry, and serve this complete range of industries. So this is what we do on the ground. Let me talk about space. We have our cryogenic radiometer and we want to measure the spectral radiance or irradiance of a sensor. So we've got our cryogenic radiometer and we can use a tunable laser to provide us a nice monochromatic source of radiation. That monochromatic radiation can be used into the cryogenic radiometer. We can measure its power and then we can use that known monochromatic beam power to calibrate the response of a photodiode at every wavelength we care to choose. And here you see an example where we're doing spectral response calibrations of a detector for space applications. Once we've got the response of a detector at all wavelengths, we have the ability to calibrate quasi-monochromatic detectors, so-called filter radiometers, which are detector spectral filter combinations, a filter radiometer, and we can do this by comparing the response of this filter radiometer as a function of wavelength using tunable lasers against this reference detector. And we can do these sorts of measurements to about 0.02%. If we've got a known filter radiometer of known spectral radiance uncertainty, we can use it with Planck's law, measure the temperature of a black body at high temperature. We know the temperature, use Planck's law, predict the radiance at all other temperatures, at all other wavelengths. Very simple, very straightforward. Here you see a black body calibrated and calibrating an instrument called CRIS, which was built by Syra, which is, and this is an image of CRIS looking at Barton Bendish in June of this year. Once we've got our black body of known temperature and known radiance, we can use it to calibrate a spectroradiometer, a monochromator, at all wavelengths, and then use that monochromator to transfer the calibration to a working standard lamp, something more convenient that we can use in the real world. And you see the traceability chain here, that we calibrate a primary standard lamp, and then we can set up working standards all the way down until we calibrate the user instrument. Space instruments and Earth observation instruments don't look at single point sources. They tend to have entrance apertures of 200-300 millimeters in size, so you need to have a relatively large aperture source to do it. And so here you see us using a specially designed source, which is an integrating sphere with multiple light sources to give a uniform source of radiance, which we can then calibrate against this spectroradiometer. And here you see one being used to calibrate an instrument called GERB, which is flying to measure the Earth radiation budget. So all of this I'm rapidly showing you to try and say this is how you calibrate a satellite pre-launch. No problem at all. Then we launch it. So where's our traceability? We have no traceability. As soon as we launch it, everything is gone. We have to try and recover that calibration in orbit. You might ask, why do we bother calibrating in the first place? Good question. But we have to recalibrate it in orbit. So we can use lamps, we can fly solar illuminated diffusers, so we can use the sun illuminating a diffuser, and if we know the output of the sun, then we can use a diffuser to give us a uniform source of which we can then recalibrate the satellite in orbit. And we can use so-called vicarious techniques, looking at the ground, looking at well-characterized sites like these deserts, so that we can transfer the calibration back to the satellite and in the end come up with our data products. Okay, there's a big problem there, as you probably indicated. This is the solution to that problem. It's a small satellite-based mission that we're proposing called TRUTHS, Traceable Radiometry, underpinning terrestrial and helio studies. A washing machine-sized satellite which has the ability to calibrate the Earth, Sun, Moon with uncertainties factors of 10 better than anything that's ever flown. And in so doing, you have the ability then to transfer its calibration through to other sensors by establishing reference targets of very high accuracy, because they're calibrated by this standards laboratory in space, and the ability to transfer that calibration to other sensors. Why am I so confident that this will work? And why it will work is because all we're doing is taking what we do on the ground and taking it into orbit. So we're transferring the ground calibration and taking it into orbit, removing all the sources of uncertainty, drift and degradation. You will recall we had our cryogenic radiometer which is our reference instrument, all that we require from this cryogenic radiometer is that it's a black detector that absorbs radiation. We can do exactly the same thing for space. We can have a cryogenic radiometer which can measure the total radiation from the sun directly with this radiometer and therefore measure total solar irradiance with no problem. We can also use it to establish a primary standard for maintenance of SI traceability. This is cryogenic radiometer for space applications. What I want to stress is that I've mentioned that all optical sensors change and degrade in orbit. Why would this optical sensor not degrade in orbit? It might. The problem is the only optical component here is an absorber which has an absorptance of 498. It can degrade by a factor of 1,000 and it will still be better than anything that's ever flown. And indeed, it's the same technology, the actual cavity absorber, which is being used for those solar measurements that I showed you early on and showed you how poor they were, but they were drifting by 0.5%, not factors of 1,000. And so we have very strong confidence that a black absorber does not change by a factor of 1,000 once it flies into orbit. So we have our radiometer that can measure total solar irradiance. We have, on the ground, we use lasers to provide our monochromatic beam to establish spectral response. We can't do that in orbit. We can't fly a suite of lasers. But what we can use is the sun. And we can use the sun dispersed with a monochromator to give us a monochromatic beam of radiation, which we can then use to put into our cryogenic radiometer. The monochromator will degrade, it will change, it will age. But because we're measuring the power coming through it, every time with this unchanging detector, it doesn't matter. And therefore, it's simply a tool to give us a source of radiation. Once we've got that radiation, we can then use it to calibrate a reference photodiode, just as we do on the ground. And then we can use that to establish the ability to calibrate a spectral irradiance device for solar irradiance monitoring. But let's look at the Earth system because that's more parallel, is that on the ground we use our filter radiometer calibrated with the tunable laser. In orbit we use our filter radiometer calibrated with our tunable monochromator. Again, the power simply monitored by reference to this traceable system, so we're just using this monochromator as a source of monochromatic radiation to calibrate the response of a filter radiometer. On the ground we have our black body. In orbit we have our sun and diffuser plate. But here, instead of the diffuser plate degrading with exposure to the sun, we're monitoring the radiance directly with a filter radiometer, looking at it directly. Therefore, drifts of the sun, absolute knowledge of the sun is irrelevant. All that matters is this traceability chain here. Once we've got our diffuser of known radiance, we can use it to expose to this Earth imager, which is viewing the Earth, a camera, and with that we can calibrate out any drift, any aging of this imager in real time every time we want to use it, achieving uncertainties of a few tenths of a percent. We can do this because we can do filter radiometers across the spectrum. And we can similarly do exactly the same thing with polarized radiometers in order to measure atmospheric contaminants and atmospheric correction, and indeed atmospheric pollutants, because they are measured by backscatter from the polarized signal from the atmosphere. Okay, how do we transfer this to global Earth observation missions? Well, by using these absolutely calibrated sensors, we can measure the sun and moon as reference targets. We can use it to calibrate other solar viewing instruments so that we can link them, the instruments that are already flying, to an absolute standard. We can establish a network of reference test sites, deserts, which are instrumented with remotely controlled autonomous sensors, perhaps the wireless networks that we were talking about earlier with small optical sensors, but in this case they will degrade when deployed, but because we can recalibrate them on an overpass with a truth satellite, we have the ability to transfer the calibration of those optical sensors, and then they can then send their information in real time via a wireless network through to the web to calibrate any other sensor as it passes over this site. We also have the beauty here that because many of these sites are used with have been used over many years, we have the ability to back correct sensors that are already flying. And so we can actually, because I mentioned at the beginning that the resolution of these sensors that are flying have a very good signal to noise ratio. It's the absolute uncertainty that's a problem. And so by correcting and calibrating these targets that they're already viewing, we have the ability to correct and establish a historical reference with lower uncertainty than what we already have. So we are able to establish a benchmark for monitoring climate change dating from 5 or 10 years ago rather than from 5 or 10 years hence. And of course, we can do some science as well, because if we've got a very good sensor, we have the ability to do very good science. I just want to show 2 more slides which effectively emphasize that we're not just concentrating on the space activities, we're also looking at trying to do improved measurements on the ground to improve the calibration of satellites. Here you see a 2-meter hemisphere with 35 cameras effectively situated on it. The aim is that this gets deployed into a field situation, something like this, but rather than on tarmac it would be on a desert or a grass terrain, and you have the ability with these 35 cameras to measure at all angles the spectral reflectance of the target that you're trying to view. In this way you can get goniometric representations of all surfaces, and by having 35 individual cameras fibre optically linked to one actual sensor, we can actually take measurements in seconds rather than the minutes and that would be required to move a sensor over this whole hemisphere. And as we all know, the sun moves with time, and therefore if you have a time movement in your measurement, you have a problem. Here is a small model helicopter. We're working with a local school to Teddington, trying to educate them into climate change, but by flying a small spectrometer onto the helicopter, we have the potential ability to do the equivalent of space-based measurements, but using a model helicopter to make ground surface measurements of the ground. At the moment, the way that ground measurements are made are by deploying people walking over hundreds of meters, carrying a spectrometer and taking measurements. Perhaps flying a small miniature sensor on a model helicopter is a solution, but it also is a solution to engage the community and engage the schools in understanding the issues of climate change. So my summary in my rapid run through is that the concept of truths as an in-flight calibration laboratory allows us to establish a system of SI traceability in space so that we can calibrate all other Earth optical sensors. This would allow us to have reference targets such as the sun, moon, and a network of ground targets. It's utilizing already implemented techniques and technology. The calibration concept can be applied to other missions. We're talking about an order of magnitude improvement in accuracy. It provides a baseline for detection of climate change. We're allowed then to quality assure the data that we have from Earth observation so that it can guarantee the decisions made by the decision makers are based on fact rather than on speculation. It allows us to identify the polluters. It allows us to improve the models and the algorithms. It allows us to truly know the impact of solar radiation on climate compared with anthropogenic effects. And I have to stress here, this step change in reduction, which is quite enormous for the space community. They don't like step change in uncertainty, they like incremental steps in uncertainty. But we achieved exactly this step change when we introduced cryogenic radiometers to the terrestrial environment back in the 80s. This is the Grail, the concept whereby we have complete traceability of the complete Earth observation system, aircraft, satellites, and ground observations, all traceable back to SI, preferably through MPL. And the last slide, I really want to emphasize this, we cannot do long-term studies of the Earth without traceability to SI units. And yep, we need to do good design for stability. We need to do good pre-flight characterization. in order to ensure that the design meets specification. There's no point calibrating something if we don't know what the ground system is. And we need to have regular comparison to a reference detector viewing the same source in order to be able to establish this traceability. And the only solution to this is a standards laboratory in space called Truths. And we want to underpin that by a network of ground targets monitored ideally by autonomous sensors transmitting to the World Wide Web. And thank you, and I apologize for taking too long. Thank you.